Welcome to Lesson 3C, OSHA PEL and Dose Response. First, I want to define what OSHA calls the PEL, or the Permissible Exposure Level. OSHA is Occupational Safety and Health Administration. It's a government agency. It can inspect work locations, sometimes unannounced, and it can levy fines if you're out of compliance. They're mostly concerned with workers. PEL, Permissible Exposure Level, is determined by OSHA. It's defined as the maximum concentration, mass concentration, or mole fraction that OSHA deems acceptable for a typical worker. They assume that the worker is working 8 hours a day, 5 days a week, so 40-hour week. The easiest way to find the PEL for any given chemical is with this nifty Online NIOSH Pocket Guide to Chemical Hazards. Here's the website. There's also a link on our course websites. What we'll do later is discuss various types of PELs. For now, we're just going to use what we call the time-weighted average PEL, averaged over 8 hours. So let me show you that website. You can pick chemicals by their first letter, so there's thousands of chemicals. So let's just look, for example, at the very first one, this alpha aminopyridine. You have all this information, the chemical formula, molecular weight, boiling point, etc. What we're interested in here is the OSHA PEL. There's also something called a NIOSH REL, which is often the same but sometimes different. This is the permissible exposure level that OSHA sets. Time-weighted average is 0.5 ppm. It also gives it in mass concentration. These are only good typically to one significant digit. So when you do the actual conversion, you wouldn't get 2, you'd get something close to 2. We'll typically use this. This one is a very small ppm. A half of a part per million is considered the acceptable level. Anything above that is considered harmful by OSHA, so this must be a very toxic chemical. I want to talk about dose response characteristics. This is in section 2.7 of the textbook, by the way. When OSHA sets these PELs, there's 3 things to consider. Body exposure. This is how much is the person, the body, exposed to. There's various chemicals. You can get chemicals through eating, through breathing, and through skin exposure. So some acid mists, etc., will affect the lungs, and they might affect just the skin, even your outer skin. So you have to look at all of these things. Body absorption is how much the body, the person's body, actually absorb. And when we say absorb, what does it mean? That it gets absorbed into the body and into the liver, maybe into the blood, etc. For eating, you might talk about how much of it gets digested rather than just going through your digestive system and coming out without being absorbed. Breathing, typically either going down to the alveoli and gets into the blood. Sometimes some chemicals actually work on even in the bronchial tubes. And then skin exposure just can get absorbed into the bloodstream typically. So there are various ways for these things to be absorbed, and body absorption. And then the body response is, how does the body react to this chemical? In other words, does it cause sickness? Does it cause death? And this will depend on the various levels, of course. Does it cause brain damage? There's all kinds of things that can happen. Some examples, if we take lead, lead is absorbed easily by the body and it stays in your body. It can cause brain damage, and there's all kinds of problems with lead, with breathing little particles of lead. Something like helium, you could breathe helium and talk funny, you talk in a real high voice, but it doesn't really get absorbed. It just comes right back out. It doesn't hurt you.
Is that because helium is an inert gas?
Good question, Ned. The answer is yes. Chemicals have everything from being very harmful to being hardly harmful at all. These 3 are related. You obviously absorb more if exposed more. If I walk into a room that has 10 times as much lead in the air, I'm going to absorb more into my body, of course. And then I wanted to just point out that PELs vary by orders of magnitude, OOM, for various chemicals. The one I showed you, for an example, had PELs of 0.5. So a low PEL means it's very harmful. And a high PEL, some PELs you look up, they could be, this might be 0.5 ppm. What we call high might be as high as 1,000 ppm or more. High PEL means it's not as harmful. So what OSHA is saying is that you could be exposed to some chemical that has a high ppm like that and not really be harmed by it. So one thing to remember is the lower the PEL, the more toxic the chemical. So a lower PEL means a more harmful chemical. So let's look at all three of these in a little bit more detail and describe each of them. So let's look first at dose, at the exposure, and we'll use dose to quantify the exposure. We'll let D equal dose, and dose is defined as the total mass of the chemical to which the body is exposed. We may not absorb all of that mass, but we're exposed to it. The dimensions of dose are mass, and the typical units of dose are milligrams. For some really harmful chemicals, it might be micrograms. We also can define D sub min, and that's called a dose rate, defined as the volume flow rate times the mass concentration min. Now be very careful here. Min does not mean minimum. It means minute, so that's confusing. Min means minute. In other words, this is the dose over a whole minute, so it's the dose per minute. Here we have Q, the volume flow rate of breathing, and C is the mass concentration of the inhaled air. Now we're talking about air quality, so we're talking about chemicals in the air. As I mentioned, you can also do similar things for eating, for skin exposure, but we're typically talking about breathing in this course. The dimensions then of this D min, it's a rate, a dose rate. So just from the equation here, QC min is the volume per time, that's Q, times mass per volume, that's C. So the volumes cancel. So this is mass over time. And the typical units of D min are milligrams, the dose per minute. The time is minutes, that's why we use this subscript min, milligrams per minute. So it's a mass flow rate. DT is the total dose, is an integral from 0 to some time t of the dose rate, QC, times dt. So this is the total dose, and that's a cumulative time averaged dose. For example, time weighted average 8 hour, you would set T equal 8 hours. And you got to be careful of your units. If your flow rate's in minutes, you got to convert to hours in that integral and make sure you have the right units. There's also a 15-minute average is also common. We'll talk about some of those later. Just to be consistent here, let's look at the dimensions of DT. Total dose are just mass, because when you integrate mass per time, integrated over time, you just get back mass. And the units of this total dose are typically milligrams or micrograms. So that's the same as dose. So that's exposure. Let's talk about absorption. The problem is that you might be exposed to 10 milligrams of some substance, but some fraction of that gets absorbed into your body. Not all of it gets absorbed. So we're going to define something that we'll talk about quite a bit now from now on here. Define MBB as what we call the mass body burden, sometimes just body burden. And this is the mass of the chemical in the body at any given time. So you're working and you're exposed to some chemical, you're breathing it, and MBB is the mass of that chemical in your body. So if you're exposed to lead and your body absorbs it, and they would take your body and melt it down and separate all the elements, they would find some lead. And if they weigh that total amount of lead in your body, maybe it's 1 milligram, that would be your body burden. All right. So the dimensions of MBB, it's a mass, it's a body, mass body burden, so it's just mass. And the units are typically, again, milligrams, sometimes micrograms. So it's what the body actually contains. And where is it? It can be in the liver, it could be in your bones, it could be in your blood, it can be just stuck in your lungs. When we talk about particles, they just get trapped in the alveoli in your lungs. It can be in all kinds of places. We're not going to really talk about where these are going. We're just looking at how much of it is absorbed. That's what we care about. And then finally, there's the response. We'll call this RP, and that is determining, does it harm you, or how toxic is it? And that's where the PEL comes in. I can absorb 1 milligram of some chemical and it doesn't hurt me at all. I can absorb a milligram of some other chemical and it might kill me. So this very much depends on dose and the PEL of the chemical that's in question. In other words, how does the body react to this chemical? The dimensions vary because there's different ways of describing the response. It's some kind of toxicity level, and you could have various ways of determining that. I'm not going to get into that here. Just want to mention something about extrapolation. You don't want to expose people to these chemicals and do experiments on them. We usually use mice and rats, and we may extrapolate. Sometimes there's accidents where people are exposed to a large amount of some chemical. So suppose you have data up here and you try to extrapolate down. There's 3 different ways here that this can happen. The first one here, number 1, is that it doesn't extrapolate linearly, but it kind of veers off towards some level. This is response. So let me just label this as more toxic, and this would be less toxic the other way. So if you have a level there where it extrapolates to, this would be something like tuberculosis bacteria. That it's been shown that even a couple bacteria, you don't need thousands of bacteria, you need a few bacteria can cause tuberculosis. So the response, these obviously have to go to 0 eventually, but even for a very tiny dose, you can have a response that's measurable. 2 just comes down linearly. You can linearly extrapolate. In that case, it's kind of the opposite. Instead of a gap here, we have a gap here, where this is a threshold where you need a certain dose before you will respond to it. A good example of that would be CO. I'm recording this on August 24th of 2020, and it seems from what I've read so far, coronavirus is like this type 2, where if you're exposed to just a small amount of it, you're not going to get virus. But if you're exposed above some threshold, and that dose, of course, depends on both the contaminant level and the time that you're exposed. So if you walk into a room and you walk out immediately, you may not get sick, even though the level of coronavirus in the room is high. Vice versa, if you are in a room for a long time with some smaller level, you might still overcome this threshold and get it. So it's hard to know how to extrapolate if you have data here. 3 is just some intermediate case between those 2, and all of these have to go to 0 here. And eventually, if you're exposed to nothing, you won't get any harm. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.